Good morning, students. So, in previous class, we discussed about the principle of working of the potentiometer, and we discussed some of the applications for comparison of EMF of the cell and finding the internal resistance of the cell. And let us see some other applications of this potentiometer are there. So, let us see those applications now. That means comparison of resistances. As I said in the last class, in the ending, I said we can compare the resistance or we can find the unknown resistance also with the help of potentiometer. Now, let us see how to compare those resistances, unknown resistance there. So, we are connecting here, and that means this is our primary circuit. Primary circuit will be as it is. There is no change in the primary circuit. So in secondary circuit, we are connecting the two resistors in series here, whose values are to be compared. That means we need to compare these two values here. So those two are connected in series, and this is another cell of some EMF IE and connected through the variable resistance. Sorry, variable resistance and through the plug key. And here this two-way plug key we use here as we discussed in the previous classes. So that means we can connect here. I am marking like X and Y, and this is the Z. So this golden meter end is Y. So then this when X and Y are connected, you can observe that then potential difference across this A and J. So this is our J here. Then potential difference across this A and J value will be equal to only the potential difference across this resistance. So then we write such a equation here, and then we are assuming like L1 is a like this L1 is a balancing length when the X and Y are connected. X and Y are connected means only that will balance the potential difference across this R1. When Y and Z are connected, then it balances the total potential difference. With this, these two are connected here, then potential difference across that AJ will be equal to, AJ means the length will changes. Previously we are taking it as L1, and now that length is L2. So that potential difference will be equal to across this R1 plus R2. So in the first case, we can write this as potential difference across this will be I. I is a current flowing in the circuit here. In the secondary circuit, we are assuming some I is a current flowing in the circuit here. So then potential difference across this we can write as IR1. So then this IR1 is equal to, we can write as X into L1, where L1 is a balancing length for this. And next, similarly, this I into R1 plus R2, the potential difference across this will be equal to X into L2. Then we can, from this, you can take the ratio of these two, and from that we can find this R1 and R2 values here. So R2 by R1 is equal to L2 minus L1 by L. So for example, if one of them are known to us, like R1 or R2 values are known to us, then we can find the other unknown resistance also. That is a way of finding the unknown resistance with the help of this potentiometer. Now let us say we can calibrate this ammeter here. So that means calibration is nothing but for this to check the correctness of this ammeter here. So then we can calibrate this ammeter with the help of this potentiometer there. Or we can calibrate voltmeter also. And so for this, the circuit arrangement will be like this. So again, the primary circuit will remain same. So cell and some variable resistance are connected across this potentiometer wire AB. And in the secondary circuit, again we are using this two-way plug key here. Then this cell of EMF E1, and this is another circuit we are connecting here. So here this resistance 1 ohm is connected here. This is 1 ohm is connected. And this is ammeter is connected here, whose that means which is to be calibrated. We need to check the correctness of this ammeter here, and a variable resistance is connected to this circuit here, right? So that means here we connect this 1 ohm here. That is important. So when we are connecting this 1 ohm here, then whatever the current is flowing through this, then when current is suppose if you are taking a resistance of 1 ohm here, if a current of 10 amperes is flowing through this. So 10 amperes current is flowing through this. Then potential difference across this means IR we can write. So which is nothing but I is 1. So then this value will get 10. That means whatever the current flowing here, then this current flowing will be numerically equal to this voltage here, potential difference here. That is the importance of taking this 1 ohm resistance in this circuit here, right? So then when current I is flowing through this circuit here, then we can write this. Again, I is the current flowing here, which is the reading of this ammeter. So this is the current is flowing here. So that is the reading of this ammeter here. So then we are taking that potential difference across that as V into, that means V is equal to IR, that R is 1. So that I am taking that as V is equal to I. And now here if suppose if you are taking this L0 is a balancing length for this cell here. for this EMF, if you are taking this as E naught here, then for this if you are taking this balancing length as L, that means when 2 and 3 are connected here, then we can write this E naught is equal to X into L, where X is nothing but we are taking it as a potential gradient. That is nothing but we are considering it as a potential gradient here. So E naught by L we can write, that is a potential gradient. Then let current I dash is flowing through this 1 ohm resistance, giving the potential difference of V dash is equal to I dash into 1, so which is X into L1. Then where L1 is a balancing length, right? That means now so now here this I dash is assumed to be the reading of this ammeter here. The reading of this ammeter is nothing but we are assuming this as I dash here. Therefore, this current flowing to this is nothing but, according to this ammeter, the current flowing to this is nothing but we need to write it as I dash. So then this I dash into 1 is nothing but equal to X into L1, right? And so therefore this here where L1 is a balancing length, when you are connecting this 2 and 3, that means when you are balancing the potential difference across this resistance, then balancing length is L1 we need to consider here. So from this you can calculate this I dash value here. So that I dash value we can write this as X into L1, right? Where L1 is a balancing length for this. And so now from this you can write this I minus I dash is equal to I minus X into L. So that is X into L1. So that X value we can write this as E naught by L. So I minus E naught by L into L1 we can write, where I is the reading of this ammeter here, right? So that is a calibration of this error. So here actually you can write that as a difference. The difference I minus I dash or I dash minus I we can write here. So that means here write this value in detail here. I is a reading of ammeter, I dash is current through the resistor. That means actual current through circuit, or that is through 1 ohm. Current through circuit means through this 1 ohm we are taking this current as I dash here. I dash is a current flowing through this, then reading of this ammeter is we are taking that as I. So then that is a calculation here. When I dash is current flowing, then potential difference across this we can write as I dash into L, I dash into 1, or this value must be equal to X into L1, where X is the potential. This is by potentiometer principle here. X into potential gradient into that potential balancing length we need to write. So by finding that I dash value, then we are finding the difference between this. That means this I dash value we are calculating from the potentiometer calculation, right? And I is a measurement of this ammeter. The ammeter will already show some reading, and I dash is we are calculating from this potentiometer here. So just the difference between them is nothing but this error in this calculation of error in the reading of this ammeter. And similarly, we can calibrate this. Calibrate this voltmeter also. So now let us see the calibration of this voltmeter here. So if L naught is a balancing length for this E naught, then this is the circuit diagram for this. So again you can observe the circuit diagram here. Here we are taking some resistance box here. So across this resistance box we are connecting some voltmeter. So that means now this voltmeter will measure like similar to our previous concept. This voltmeter will measure directly, that indicates one reading, and we calculate, that means across this resistance box, and we calculate that same potential difference by using this potentiometer circuit here. Then we find the difference between them. That means how much calibration or how much error is there. So that means for this cell we are taking this balancing length. That means when by connecting 1 and 2, if you find the balancing length, then you will get the potential difference across this the potential EMF of the cell you can calculate here, so which is nothing but this E naught. So then E naught is equal to, we can write that expression as, by using our previous principle of potentiometer, E naught is equal to X into L naught we can write here. So from this again we are finding this potential gradient, right? So that is a potential gradient there. So next here we connect this 2 and 3 here. So by connecting this 2 and 3, now this potential difference across this AJ will be equal to potential difference across this resistance box. So let's suppose some I is the current flowing through the circuit here. So then potential difference across that we can write as x into L1 if L1 is the balancing length here. And so then this value we are writing as E naught by L naught into L1, so which is nothing but this equation here. Then we find the difference between reading of this is the now this value is calculated by using this potentiometer, and this V is already the reading of this voltmeter here. So now these values we calculate here, the difference here. So similar to our ammeter reading, here it may be V minus V dash may be there, or V dash minus V value we may write, larger minus smaller value we need to write. And so that's what they are saying here. It may be positive, negative or 0 they are saying here. So that means if you are finding exactly this value, reading of this voltmeter minus reading of reading from the potentiometer, then it may be positive or negative or 0 they are mentioning here. That means the value of the difference between the reading of the voltmeter and the reading of this potentiometer here, right? And now let us see some differences between the potentiometer and voltmeter. So we know already this voltmeter is already used to find the potential difference between the different between 2 points, or we can measure the EMF of the circuit, and by same application, that means the same thing we can also measure by this potentiometer, and we said potentiometer is accurate when compared to that of voltmeter. So now let us see some differences. What are the major differences between the voltmeter and potentiometer here? So now if you observe this voltmeter here, then you can observe this its resistance is high but finite. That means the resistance of practical voltmeter, ideally it should be infinite, but practically it is high but finite value will get. So its resistance is infinite because here no current will flow through that. That means this is based on the null deflection here. Whatever the reading you are measuring by using potentiometer, it is measured by this null deflection method only. That means galvanometer indicates a 0 reading. So that method is also called null deflection method. So null deflection method means no current is flowing. No current is flowing means you can consider that as infinite resistance. It draws some current from the source of EMF. That means if you want to measure EMF of a cell, we connect a potential voltmeter across that. Then this voltmeter will draw some current from that because its resistance is finite, not infinite. And so then the error will be there. So it does not draw any current from the source of the unknown EMF. We know in secondary circuit, if you connect a cell to find its EMF, it doesn't draw any current from that. That means no current flow through the cell. So that automatically it gives a more accurate value. Potential difference measured by it is lesser than the actual potential difference here. So this value we know already. The voltmeter will give a value less than this actual value. Potential difference measured by it is equal to the actual potential difference because it does not draw any current from that main circuit. So it gives a more exact value there. Its sensitivity is low and its sensitivity is high. It is a versatile instrument. It measures only EMF for the potential difference there. And so, but whereas this voltmeter, you know, voltmeter can be converted into ammeter, like a galvanometer setup there. So we can convert it into ammeter, or we can increase the range of the given voltmeter. So it is based on the deflection method. So this galvanometer deflection will be there. So by measuring the deflection, we measure the potential difference here. But whereas for this, the deflection will be 0. Whenever you are using the potentiometer, the deflection, whether you may measure the resistance or EMF or potential difference, that the deflection must be 0 only. Then only we take the readings of this, we do the calculations from this potentiometer there. So those are the major differences between voltmeter and potentiometer, right? So that is about the different applications of the potentiometer and principle of this potentiometer. Now let us see some problems based on this potentiometer. And now let us see a simple problem based on this. So in a potentiometer experiment, the balancing length of the cell is 560 centimeters. And when the external resistance of 10 ohms is connected parallel to the cell, the balancing length is changes by 60 centimeters. So find the internal resistance of the cell. And so for the internal resistance, we already derived a formula in the last class. So then R is equal to this capital R into L1 minus L2 by L2, right? This is our formula for this internal resistance here. So this L1 is a balancing length before connecting this external resistance, so which is 560 centimeters is given here. Now this L2 value is given as its value is when 10 ohm resistance is connected here, then it changes by 60 centimeters is given here. Changes by 60 centimeters means when you are connecting this external resistance, then instead of EMF of the cell, we need to measure the potential difference across the terminal voltage, so that this balancing length will decrease. So we need to remember this point here. So that means exactly for this type of questions, you need to remember this. That means even though you know formula, you may not get the correct answer if any confusion is there. That means if you are adding that, for example, changes means you may think either increasing or decreasing. So remember that whenever after connecting this external resistance, balancing length will decrease, because before connecting that resistance, we need to balance the potential EMF of the cell across that AJ, the balancing point, the balancing length. But once if this resistance is connected, then current is flowing through that cell, and so only we need to balance this E minus IR value, terminal voltage. So as this potential difference is decreasing, and there also balancing length will decrease here, and so then this value you need to take it as 500 centimeters. So that is the only point you need to note here. Then after that you can substitute these values in this equation. R is equal to 10 ohms is given. So you need to substitute those values, then you will get this internal resistance as 1.2 ohms, right? And so now let us see this another problem based on that. So in an experiment with the potentiometer, the measuring the internal resistance of the cell, when the cell is shunted by 5 ohms, the null point is obtained at 2 meters. When the cell is shunted by 20 ohms, the null point is obtained at 3 meters. The internal resistance of the cell is. So that means now here we are connecting the two different resistors there across that. And so our formula is like R is equal to capital R into L1 minus L2 by L2, right? So that means now when R is equal to connected as 5 ohm resistor here, therefore you can consider this value as that means that balancing length, let us take it as L2, and when R is equal to 20 ohms, then this balancing length, let us take it as L2 dash. So then let us substitute those values in this equation here. So then R is equal to 5 into L1 minus L2 by L2, and this is equal to, and these values are given here. I will substitute that. So then this is 20 into L1 minus L2 dash by L2 dash, right? So that means L1 is a balancing length before connecting that resistance. So it does not depend on whether you are connecting 5 ohms or 20 ohms. So L1 value will remain same. So this L2 value only is changing here, that we are taking it as L dash. And so then you can simplify this. Then this value is 4, and I am substituting the given values here. So L1 minus this L2 value is given as L2 value is what is the given value of 2. This L2 value is 2 meters. So L2 value is 2 meters and L2 dash is 3 meters here, right? So then let us substitute those values here. So L1 minus 2 by 2, I am substituting in meters only. So L1 also will get in meters only. And this is L1 minus 3 by 3 into 4. And then simplify that, then you will get this L1 value here. And by substituting L1 value either in this equation or in this equation, you can calculate this resistance here. So then just by cross multiplication, 3L1 minus 6 is equal to 8L1 minus 8 into 3, 24. And so from this you can write this as 5L1 is equal to 18, right? Yeah. Is L1 is equal to 18 by 5 you will get here. So which is nothing but you can write this as 3.6 meters. Now therefore this R value we can substitute here. Therefore it is 5 into, this is 5 into L1 is 3.6 minus this L2 value is 2 by this 2. So therefore it is 5 by 2 into, this is 1.6 by 1.6 here, already we are writing this 2 here. So therefore it is 5 into 0.8, so which is nothing but 4 ohms. So that 4 ohms is the internal resistance of this cell, right? So like this, based on this actually potentiometer, majority of the problems will be like based on this formula only. That means you need to understand that given data correctly, and then you need to apply that proper formula here. So let us say this: a cell having the steady EMF of 2 volts is connected across a potentiometer wire of 10 meters length. The potentiometer wire is of magnet and having a resistance of 11.5 ohm per meter. So that means here resistance per unit length is given here. So you need to observe this given unit here. This is given as ohm per meter. This value given is ohm per meter is given here, right? And so that then another cell gives a null point at 6.9 meters if the resistance of if a resistance of 5 ohms is put in series with this potentiometer wire, then find the new position of this null point. So that means initially that series resistance is not there in our potential in the primary circuit. Now they are adding that series resistance there. So length of this potentiometer is given. Now follow this potential dropper meter. That means potential gradient we are calculating here. That means in the primary circuit there is no any resistance. Only the resistance of this cell will be there. Like suppose if you are taking a circuit like this. So if you are taking a circuit like this, here there is no any resistance here. Then only the resistance of this wire will be there. So this problem is the first case is given like that. And so that then directly we are taking the EMF of cell in the primary circuit by this length we are taking here. So that gives a potential gradient, potential drop per unit length. That means in our general formula, we are writing this potential gradient as like suppose if you are taking this as x, then this is nothing but I into R by L we are writing, where this I is nothing but EMF of cell in the primary circuit plus R plus RH plus small r we are writing here, right, into this R by L we are writing. So here this small r value is RH value is 0 and this small r value is also 0. Both are 0 here. So only this E by R into R by L, then this R and R value will be cancelled, E by L. So directly we are writing that E by L value here. So that means this RH and R values may be 0. That depends on the given data there. Right. So here no information is there regarding the series resistance, means we can take that value as 0. And now since the cell gives a null point at 6.9 meters, the EMF of the cell. So then EMF of the cell in the secondary circuit we are calculating here. So that this balancing length is given. So potential gradient into balancing length, that gives us EMF of the cell. So 1.38. Now resistance of the potentiometer wire. So as I said here, you need to observe here the resistance itself is given as 11.5. So directly without reading it carefully, if you are taking the resistance of the wire as 11.5, you will get the wrong answer. So you need to observe the units carefully here. So then resistance of that wire is resistance per unit length into length of the wire you need to write. So which is 115. When the resistance is 5 ohms is connected, then total resistance. So that means now in the series resistance we are connecting. That means RH value now is 5 ohms we are connecting here. So the total resistance in the primary circuit will be 120 ohms. Then I value we are writing. That means this value we are calculating here. So that value is nothing but E by that means E by this R plus R we are writing here, total resistance. So that means that's value you will get. Now the potential gradient we are writing here. That means just this value we are calculating here. This value, that means I value we calculated, and R by L value is already 11.5. So we are substituting that value. So you will get the potential gradient. Then this null point should be, that means this EMF of the cell must be equal to again this potential gradient into new potential gradient. Now the potential gradient is changing here into this new balancing length. So from that we can calculate the new balancing length there, right? So now let us see this another problem based on this. So a battery of EMF 2 volts and negligible internal resistance are connected across the uniform wire of length 10 meters and resistance 30 ohms. Now here you can observe the total resistance is 30 ohms only. A appropriate terminals of the cell of EMF 1.5 internal resistance 1 ohm are connected to the one end of the wire, and other terminal of the cell is connected to the sensitive galvanometer and to the sliding wire. What length of wire will be required to produce a zero deflection in the galvanometer? How will the balancing changes? When the coil of resistance 5 ohms is connected in series with the battery, and a cell of EMF 1.5 ohms is shunted by the 5 ohm resistor, right? So that means now here three different questions are there. First they are asking just for this balancing length for this cell here. So same, we need to find the potential gradient, and then potential gradient into balancing length will give us this 1.5, that means EMF of the cell. So potential gradient we are calculating here. Here again similar to our previous problem, you can observe this negligible internal resistance. So negligible internal resistance is there here, and there is no series resistance. That means in this problem also internal resistance is 0, and this RH or RS value series resistance is 0. And so that here also this potential gradient means you will get this directly, this EMF of the cell by length you can write here. So then that is nothing but what they are writing here. So 2 by 10, so which is 0.2. That is the potential gradient of this. And so now this 1.5 must be equal to potential gradient into balancing length we need to write here. So therefore balancing length you will get this value as 7.5 meters. And next they are asking that when 5 ohms is connected in series with this battery here. So that means in series with this battery. Now this problem is also similar to this part only, right? So now we are connecting in series with this, we are connecting a resistance here. When you are connecting a resistance, then automatically the current in the circuit will changes, and thereby potential gradient also changes here. So again we need to start from the beginning here. So again this value total current we need to calculate here, and from that we need to calculate the potential difference there, right? So you can calculate directly like this. Instead of doing that calculation, you can write this as 2 by the total resistance we need to write here. The resistance of the wire is given as 30, and so then this is plus 5. So total 35. This is the current here. And therefore this potential gradient we can write this as this x value, we can write this as I into R by L we can write. So that means it is 2 by 35 into this potential is 30 and resistance is 30 and this length is 10. And so that it is 6 by 35 you will get, right? So that is the potential gradient there. So potential gradient is nothing but this value. And then now this EMF of the cell, we need to write the balancing length now. The balancing length you can write this as potential gradient into this value. That means this 6 by 35 into L1 is equal to 1.5. So from this we need to calculate this L1 value. And next similarly that value is connected in parallel there, in parallel with that circuit, right? So that means that is another third case given here. Now we are connecting this 5 ohm resistance like this. And so then this is nothing but similar to that of determination of the cell here. So we need to calculate the potential difference across this. That means terminal voltage we need to calculate here. Even though this galvanometer given here shows a 0 reading, there will be some current flowing through this. And so let us calculate that current here. So that current we can write as 1.5 by only in this circuit. 1.5 by total resistance will be 6 you will get, right? So which is nothing but this value is nothing but we can write this as 1 by 4. So 1 by 4 amperes. And then now this terminal voltage I am writing here. That means terminal voltage is nothing but potential difference to be balanced here. So the terminal voltage we can write this value as V is equal to E minus IR value we can write. You need to observe here when current is flowing here, the potential difference across this AC2 must be equal to terminal voltage, potential difference between the two terminals of the battery. Since current is flowing through the cell is now in discharging state. So discharging state means the terminal voltage is nothing but E minus IR. So 1.5 minus this is 1 into 1 by 4. So this value you can write this as 3 by 2 minus 1 by 4. So which is nothing but so 5 by 4 we can write, right? So 5 by 4 volts. So now this value is to be balanced across this. Therefore this 5 by 4 I can write this as 5 by 4 is equal to, so 5 by 4 is equal to potential gradient. Potential gradient is we already calculated here 6 by 35 into some L we need to write here, the balancing length. So from this we need to calculate this L value there. So it is 35 into 5 by 24. So that gives us balancing length there, right? So that means like that we can calculate this balancing length here. So this is the balancing length, but actually here just a minute, the given case is actually, let us go back to the question here. In the part C, read this question here. So this 5 ohms is in series only in the part B. So in part C, this 5 ohms, the same 5 ohms we are connecting in parallel there. So our calculation is wrong here, because here this series 5 ohm resistance is not there. We are calculating according to that. That means we are taking this say this potential gradient, we are taking this value here. So not this one. We have to take this first part here, because this 5 ohms is not there. So then here potential gradient is 0.2. So that value now we need to take here. So that means here this potential gradient is mistake here. This value we need to take this value as 0.2. So that means 0.2 into L we need to write here. So that L is nothing but, now we can write this as 25 by 4 we can write. And so that you will get like 6.25 meters you will get. So that is a value here. So note here. That means this is nothing but the same 5 ohms. Instead of connecting in series here, we are connecting in parallel here. So when it is connected in parallel, then how that resistance, that means that balancing length is changing. That's they are asking here. So that means now here again this circuit here, there is no resistance except this resistance of this wire. So potential gradient will be only 0.2 you will get, right? And so now let us see this problem here. And so now in this problem, if you observe this, consider this potentiometer circuit arranged as shown in the figure. The potentiometer wire is 600 centimeters long. At what point, at what distance from the A should the jockey touch the wire to get the zero deflection in the galvanometer? If the jockey touches the wire at the distance of 560 centimeters from A, what will be the current in the galvanometer, right? So this circuit is shown here. This is L of EMF E and resistance R is given, and this is in secondary circuit we are connecting a cell of internal resistance, say some E by 2 is given, and this EMF is E by 2 and internal resistance R is given, and this is a galvanometer connected in series with it. And total resistance of this potentiometer wire is also given as 15 R. That is the given data here. The circuit is given data. And so now C is the balancing length we are considering here. Therefore, this potential difference across that length we are writing here. So potential difference across that length is nothing but I into RC we are writing here. So potential difference across this C. Suppose if you are getting this balancing length at this point here, right? So if you are getting this balancing point at this point, then potential difference across this we can write like this. And so now the potential difference EMF of the cell is equal to this potential difference by the length, potential gradient. This value we need to divide with this length here, 600 meters, and then into this balancing length we need to write here, right? So then we are substituting this value here. So potential difference across this AC value will be equal to E by 2 is equal to, this is potential difference across this AC, this wire. So this wire calculation, you know, potential gradient IR value, and from this divided by length into multiplied by this balancing length we need to write. So from this you will get this L value as 320 centimeters, right? So that means this balancing length, this EMF E by 2 will be balanced across 320 centimeters of this length. So this next part is important for us. So then when, but in the next part what they are asking is, we are touching this jockey at a distance of 560 centimeters from this wire. So that means at just if you are taking it 320 centimeters, then this EMF E by 2 will be balanced by this potential difference across this. Now here we are touching at some other point here, which is some 520 centimeters, 560 centimeters. So then definitely we can say that now potential difference across this AC will be greater than that of this EMF of the cell, right? And so now current should enter into this. So their EMF will be more, and so current should enter into this positive terminal of the battery here. So now they are asking this current here, how much current is flowing here. Just you need to take this Kirchhoff law. Just by applying the Kirchhoff law, now we can solve this. So this is the current distribution what we are assuming here to apply this Kirchhoff law. So observe this here. I know this is the current in the primary circuit. Means from this primary cell in the primary circuit we are taking here. Out of this I is the current flowing in this direction we are taking here. So that this remaining current I minus I naught will flow through this part here. And so now this length again this total, these two will join here. So that the total current I naught is flowing here. And so next what we are calculating is resistance of 560 centimeters of this wire we are calculating here, because we are touching this, we are making this contact at 560. So we are taking this length here, the resistance of this length we are calculating. 15 R is the resistance of 600 centimeters. So resistance per unit length into length of this part we are writing. So you will get 14 R. So remaining this R will be there here. So the total length is 15 R. Now just apply the Kirchhoff laws here. Just by applying Kirchhoff laws you can calculate this I value here. So first we are applying for this loop here. That means this 1, 2, 3, 4, 1. This loop we are applying here. So this is minus E by 2 minus IR, and here galvanometer is taken to be ideal. Here there is no resistance of this galvanometer because it is not mentioned in our data there, right? So then this is resistance of this wire here, plus we need to consider we are traveling opposite direction. So plus 14R into I minus I naught minus I we can write. So then this is one equation here. And next we can apply for this equation like 1, 4, 5, 6, 7. That means for this primary circuit we are applying here. So let us apply for this. So then minus 14R into I minus I naught minus I. And here you will get this minus I naught into R. And again this is minus I naught into R. And plus E by E you will get. And you will get this another equation here. By solving these two equations you can find this I value as 3E by 22R you will get. So it is a finding this. If the jockey touched at any other point other than the balancing length, there will be some current flowing through the galvanometer. So if you want to find the current flowing through the galvanometer, this is the procedure here. You can apply the Kirchhoff laws to find that current, right? If there is touched at a point less than the balancing length, then this current also will flow here. That means this direction already, with the knowledge of this balancing point, you can decide the direction of this current here. Even if you are getting confusion, you know, in Kirchhoff law there is no problem regarding the direction of the current. You can assume the current direction anyway, right? And so now let us see this paragraph question here. This is important model. A thin uniform wire AB of unknown resistance is connected between the points AB. So this is unknown resistance here, AB. So AP and QR. These are QR, or the thick conducting strips. A battery of unknown EMF E and a galvanometer with the sliding jockey connected to it are available. That is not shown here. This is available. That means secondary circuit part here. Connections are made to find the EMF E and the resistance of the AB and the length of the wire AB. The battery with the galvanometer is connected between the points A and B in two ways, such that jockey when pressed on AB wire at a distance of 80 centimeters and 120 centimeters respectively from the end A, galvanometer shows zero reflection. That means between 2 points we are connecting the galvanometer and the jockey in two ways here. So once that means in one way, if you are pressing it 80 centimeters, we are getting zero deflection, and next in another way, when you are connecting in another way, when you are pressing again at 120 centimeters, you are getting the balancing point. And next series, one end of the battery with the galvanometer is connected to the point R. That means next here we are connecting here, and the jockey pressed on the AB at a distance of 180 centimeters from the end A. Deflection the galvanometer is zero. That means when you are connecting one end of this jockey here, then when you are pressing it 180 centimeters, then we are getting this balancing point there, right? So those are the three cases are given here. So now let us see the questions regarding this. So find the length of this wire. So this length of this wire AB they are asking here. So two ways they are connecting here. This is a one way, our usual way. The positive terminal is connected here and the galvanometer is connected here, so that the balancing length is obtained at 80 centimeters here, right? And so now we can write this balancing length for this. That means the just equation, our general procedure you can write here. This EMF of the cell is equal to 15 by the total resistance here. So here let us take this resistance as R, and these are already given here. So then these two are in series. So 5 by 3 you will get. So 5 by 3 plus R into this is I value you will get. So I into R by L. This total length of this wire which is unknown, and this balancing length is 80, right? And next, when battery is connected to this another point B here, that means here we are connecting it in another way. So to connect it in another way, the procedure is actually here. We need to connect like this. So I will show here how to connect this. So we need to connect this value like this. Now the positive, that means negative terminal of the battery will be connected to this point B, and the positive terminal is connected here. Now the jockey is connected like this, and now the jockey is pressed at this points here. That means at some different points here until you will get the balancing point. So now the another way means this is another way here. Negative terminal is connected to this point B, and the positive terminal and the jockey are connected like this, so that we press the jockey at different points. Then they are giving here is at 120 centimeters from this A. This 120 centimeters from this A, then we are getting this balancing point here. Suppose now if you are getting this balancing point at C, for example, if you consider, then in this case the potential difference across AC is not equal to EMF of the cell, right? The potential difference across this BC will be equal to EMF of the cell here. So that is the important thing you should note here, because we are pressing it like this. So then these two are connected together here. So then potential difference across this BC must be equal to the EMF of the cell. So that's what we are writing here. So then IR, the same calculation here. Just this length will be, instead of this taking this length, you need to take this length here. So L minus 120. And just by solving this equation 1 and equation 2, you can calculate this length here. The balancing, that length of this wire AB is nothing but 200 centimeters you will get, right? Or you can directly say that from this side we are getting 80 centimeters and from this side you are getting 120 centimeters. Then total length of the wire is nothing but you will get like 200 centimeters. The directly you can say that this is experimental procedure for this. And next, the resistance of this wire AB they are asking here. So from this equation, as we calculated this balancing length, that means length of this wire AB, you can substitute this length here, and so that from that you can calculate this resistance there. So see this, the next question is about this resistance of this wire AB only. So then if we substitute that, you will get one equation in terms of this R here. So just we are substituting this L value in the previous equation. And now let us write this. Another condition is given for us. The another condition is nothing but when R is, that means battery is connected to the point R, then again this balancing length is given here. That balancing length is nothing but, you can observe here, 180 centimeters here. So now let us write the equation for this. So when it is connected across this 180 centimeters you are getting, means then this is 180 centimeters here. This length is 180 centimeters. So that means only this length will be 20 centimeters, because we already calculated this length as 200 centimeters. Then potential difference, that means the EMF of the cell will be equal to potential difference across this 20 centimeters plus this potential difference across this 1 ohm here, because this is connected across this. So EMF of the cell will be equal to potential difference across 20 plus potential difference across this 1 ohm. So that equation we need to write here. So this is the I value we are writing here, 15 by 5 by 3 plus R into this R value we are writing here, the IR value. So R is nothing but here this 1 ohm, and for this we are writing this R value here, R by 200 into this length we are writing here. So then by solving this equation 1 and equation 2, or equation 2 and equation 3, that means either of this equation we need to take and we need to combine with this equation 3. So by solving those two equations you will get this R value here. By substituting this R value here, you can calculate this EMF of the cell here. So which is nothing but our next question here, EMF of the cell. So this R value you can substitute in any of our equations 1, 2, 3 here, then you will get this that unknown EMF here. So that R is equal to 10 by 3. By substituting the 10 by 3 here, we are getting this EMF of the cell as 4 volts. So that is the EMF of the cell here. So those are some problems based on this potentiometer. That means most of the problems regarding the potentiometer will be like calculation of that potential gradient. So potential gradient calculation is very important in this potentiometer problems there. So potential gradient calculation and then balancing that potential gradient across the EMF of the cell in the secondary circuits, right? So these are some problems, and practice the remaining problems from the material and other worksheets which I solved soon. So then by solving those problems, then you will get a more idea about this. So as I said, these meters part are very important for the competitive examinations, and then these are very easy also. Just you need to understand the questions carefully there. What are the given resistors, and especially regarding this potentiometer about the series resistance. So don't confuse about the series resistance. It may be, sometimes it may be 0 if there is information given there, or we need to take some resistance when some resistance is given there, right? So then read the total data wherever the given resistors are there. Read the total data carefully, then you can solve these questions easily. Just once if you know the total derivations regarding this potentiometer. So practice the total derivations regarding the potentiometer, either calculation of internal resistance or finding the EMF of the cell or comparison of the EMF of the cell. So practice all those derivations by your own, then automatically you can solve these problems easily, right? So practice these problems based on this. Thank you.